Hey everyone, and welcome. Ever just looked at a beam of sunlight and thought, what's really going on in there? Well, it turns out it's hiding some pretty amazing secrets. Today, we're going to unlock them, revealing not just a hidden rainbow, but a whole family of invisible light. Let's dive in. So let's start with a really simple question. Is white light, well, is it just white? You might think so, but it's actually so much more. That one simple beam of light is really a wild mixture of every color you can possibly imagine, all mashed together. All right, so here's the game plan. We're going to start with a prism secret rainbow, figure out why light even splits in the first place. Then we'll look beyond the light we can see. And to wrap it all up, we'll explain the sky's light show and finish with a quick quiz to see what you've learned.
Okay, first stop on our journey. We're going to look at a pretty simple but super powerful tool, a glass prism. Yep, this little triangle of glass is the key that's going to unlock all the hidden colors inside white light.
You know, this magic trick that the prism does, it has a cool scientific name, dispersion. Just think of it like this. White light is like a smoothie made of a bunch of different colored fruits, all blended up. Dispersion is the process of, well, unblending it, splitting it back into its original colors so we can see every single one.
And get this isn't some brand new discovery. We're talking way back in the 17th century. Sir Isaac Newton himself did this exact experiment. Imagine him in a dark room, letting just a tiny beam of sunlight shine through a prism. And, boom, on his wall a beautiful band of colors appeared. He's the one who called it the spectrum, and we still call it that today.
Now you'll notice something really specific about these colors. They're always in the same order. And there's a super easy way to remember it, the acronym VIBGYOR. That's violet, indigo, blue, green, yellow, orange, and red. It always runs from violet at the bottom, which gets bent the most, all the way to red at the top, which, you guessed it, bends the least.
Okay, so we've established that a prism splits light. But the big question is, why? What is actually going on inside that little piece of glass? Well, it all comes down to a race. Yep, a race between the different colors of light. Let's break down how that works. All right, here's the absolute key to understanding this. In the vacuum of space, all colors of light are speed demons, traveling at the exact same incredible speed. But the second they hit something different, like air or water, or in our case, the glass of a prism, they all slow down. And here's the kicker. They don't all slow down by the same amount.
And this is how that race plays out. You've got red light, which has a nice, long wavelength. It's the speedster of the group. It travels the fastest through the glass, so it doesn't get bent very much. Then you have violet light on the total opposite end. It's got the shortest wavelength, making it the slowpoke of the bunch. Because it's so slow, it gets bent the most. It's this difference in bending, from the least to the most, that fans all the colors out into that amazing spectrum. All right, so we've cracked the code of the rainbow. Pretty cool, right? But I need you to brace yourself because what I'm about to tell you is a real mind bender. That rainbow, the entire VIBGYOR spectrum that our eyes can see, is just a tiny, tiny little slice of all the light that's actually out there. So that begs the question, right? If there's all this light we can't even see, what is it? What does it do? The answer to that question is going to take us on a tour of the much, much bigger electromagnetic spectrum.
Just take a look at this. You see visible light, our little rainbow, just sitting there in the middle. But look at all its family members. We're talking about invisible forces we use every single day. Gamma rays to fight cancer, X-rays to see broken bones, ultraviolet light to sterilize equipment. And on the other side, we've got infrared for your TV remote, microwaves to cook your food, and radio waves for, radio and TV. It's all light, just different flavors that our eyes can't pick up on. Okay, let's bring all this physics back down to Earth for a minute, because now that we know all this, we can actually use it to solve a huge, everyday mystery. Why is the sky blue? To solve this, we need to introduce one last piece of the puzzle. It's a concept called scattering. Imagine sunlight as a bunch of tiny balls hitting our atmosphere. The atmosphere is full of even tinier particles, like little pinball bumpers. When the light hits these particles, they absorb it for a split second and then just spit it back out in every possible direction. They scatter it. And here is the most important part of that whole process. Not all colors play this pinball game the same way. There's a rule here. The shorter wavelengths, our friends blue and violet, they get scattered like crazy. They bounce all over the place. But the longer wavelengths, like red and orange, they're much better at just plowing straight through without getting knocked off course. And that right there gives us the simple, step-by-step reason for a blue sky. So, step 1, sunlight with all its colors hits the atmosphere. Step 2, the little air molecules start scattering it. Step 3, they go absolutely nuts, scattering the blue and violet light way more than any other color. And finally, step 4, our eyes look up and see all this scattered blue light coming at us from every direction. And voila, the whole sky looks blue.
Now, what's really cool is that this exact same idea explains why we get those beautiful red and orange sunsets. Think about it. At noon, the sun's directly overhead, so its light travels through the least amount of atmosphere to get to you. But at sunset, the sun is on the horizon. Its light has to travel through a ton more atmosphere to reach your eyes. By the time it gets to you, almost all of that blue and violet light has been scattered away from your line of sight. So what's left? You got it, the longer wavelengths, the reds and oranges, which come straight to you. Whew, okay, we have covered a lot of ground here, from prisms and VIBGYOR all the way to why sunsets are red. So let's do a super quick recap of the main points and then test your knowledge. So if you remember anything, remember these 3 things. First, dispersion. That's white light splitting into VIBGYOR, because each color has its own speed in a prism. Second, the EM spectrum. The rainbow we see is just a tiny piece of a huge family of waves. And third, scattering. The sky is blue because our atmosphere is way better at scattering short blue wavelengths than long red ones.
All right, pop quiz time. First question for you. Thinking back to that prism and VIBGYOR, which color gets bent the most? Remember, it's the slowpoke of the group. Got it? If you said violet, you are absolutely right.
Okay, next one. This is a real-world question. Using what we just learned about scattering, why do you think stoplights and danger signals are always red? I'll give you a sec. It's because red light scatters the least. That long wavelength allows it to cut through things like fog and rain, so you can see it from farther away. Super important for safety, right? And for the final question, let's go back to that big electromagnetic spectrum. Can you name one type of radiation that has a wavelength even shorter than visible violet light? Any one of them will do. If you thought of ultraviolet, X-rays, or gamma rays, you nailed it. You know, we'll leave you with this amazing quote from Albert Einstein. The whole of science is nothing more than a refinement of everyday thinking. And that's so true, isn't it? The next time you see a rainbow or just look up at the blue sky or an incredible sunset, you'll know the incredible physics behind it. It all starts with just being curious about the world.